Now, it's not hard to understand why, if we increase the pressure in the bottle quickly, so quick increase in pressure, we actually increase the temperature of the air in the bottle. Now, that increase doesn't last long because the bottle exchanges heat with the air, the bottle being kind of thin. The heat with the air in the room pretty much equalizes the temperature fairly quickly after we've done a quick squeeze. But there is a temperature increase. A temperature increase because the walls are moving in on the molecules inside the container. So in the collisions of the moving wall with the molecules in the molecules in the container are sped up. We'll see the details of that. We're not going to deal with that right now. But if we want to increase the pressure in the bottle at a constant temperature, we want to increase it slowly. Okay? A slow increase in the pressure allows the temperature to continually equalize itself, or very nearly equalize itself, with the temperature of the air surrounding it. Okay, well, the question is, how much work is done at constant pressure when we, how much work is done when we expand a gas at constant pressure? We've seen already that that's P delta V. If the pressure is not constant, then the work, as we saw by simply forming a Riemann sum of T delta V over small increments of volume and taking the limit, we get an integral from initial to final volume of pressure with respect to volume. So the L1 question says if the pressure of confined gas increases at constant temperature, then according to the ideal gas law, what's the expression for the pressure? And then what's the integral of that expression? Well, the expression for the pressure at at any temperature, the expression for pressure is nRT over V by the gas law. And if we have constant temperature, and of course a confined gas sealed container so that N remains constant, then the pressure is a function only of the volume, and R and T are invariant, so that our integral, our work integral, is from volume 1 to volume 2 of nRT over V. In the case where N and T remain constant, we can bring the nRT outside the integral, and we can perform the integral, and the integral is very straightforward. Once we have the constants out, we're just integrating 1 over V with respect to V. The result is natural log of the absolute value of V, which is evaluated between the two limits, the volume limits, V1 and V2. And that's nRT times the natural log of V2 minus the natural log of V1. Now, I've erased, but not very well, of course, this being a chalkboard, I've erased the absolute value signs because we don't need them. Since there's no such thing as a negative volume, the absolute value of the volume is just the volume. So we get the natural log of V2 minus the natural log of V1. The laws of logarithms tell us that that's the natural log of V2 over V1. So this is the expression for the work done when a gas is expanded at constant temperature, where a confined gas is expanded at constant temperature.